recording that will hopefully help you with expediting the work on your project. First piece of advice: read the grading scheme carefully. Make sure you don't lose points just because you haven't provided references and the formatting side. Okay, and then you'll have to choose the material, the aluminum material. I have to choose the everything else here, and also observe this kinematic diagram. At the end, you will have to draw this at scale, so that the mechanism is at scale. The gear represented by just the pitch circle, and the pinion are at scale, and the belt transmission, the sheave, and the belt and center distance between the two sheaves. You see here current displacement and start of punch, end of punch displacements. You can assume the punch length to be 0 in many of the calculations where you'll be or you're doing the kinematic diagram and analyze for position, velocity, and acceleration the punch in this configuration, that is punching downwards. In the notes you had a slider crank mechanism. We have a slider crank mechanism that was analyzed, but punch was moving horizontally. Don't forget, there's an eccentric slider crank mechanism, so if you draw a line, it's not, this appears to be centric, but it's in a positive eccentricity will be to the right. Okay, so the line of sliding through the center of this pin joint is not also through the or it's not the y-axis, not through the ground joint about which the crank rotates. Okay. And the requirements you have to for the midterm project report, you need to select the motor up to point 11 and then the rest, which are quite involved. I'm telling you now, the 12 to 17 steps of the project will take you quite some time to perform. Okay, so here I'm making, please read this. So I'm making you some recommendations how to search to write the introduction to your project, and I have supplied a sample screenshot to show spreadsheet organization, and then how the working model should look to validate your calculations in the Excel work. Not shown here, but and I'm emphasizing this, you have to generate position, velocity, and acceleration of the punch in Excel and have them side by side to validate your use working model to validate the Excel part. This is the transmission angle, which same as for the punch moving vertically. Same was the theta 3 angle. So you have again theta 3 dot, theta 3 double dot. A quick way of checking for correctness is to have velocity going to 0 where you have the limit positions, and acceleration going to 0 when you have minimum and maximum velocities. And likewise here, known thing, derivative goes to 0 where you have minimum, maximum. And then some more information about the part 2 of the project with the shaft calculation and gear calculation. I'll have separate recordings for bell selection and more on the latter part of the project. Okay, so if you go to the notes, let me minimize this. I said minimize. So if you go to the notes, you have an eccentric slider crank or crank slider mechanism. Crank is the input, slider is the output. Slider crank would be like in a piston engine, where piston is the input. Anyway, so you start a vector equation, the corresponding scalar equations. You solve, you square, you add them, you get a quadratic in the unknown S. And in my spreadsheet, in the sample output that you saw, okay, so there is a B and C. Well, B and C are so A would be 1, B is the multiplier for S less the 2, and C is the free term in the quadratic. In order to, and you can do this, add intermediate columns with intermediate results to make it easier to organize, to debug the spreadsheet. So here's the quadratic. You can see negative 2bx plus c, although the unknown is s in your quadratic. Okay. For velocity, you differentiate the scalar equation. That's the two scalar equations, and you get a system of equations, a linear system, two unknowns, s dot and theta 3 dot, and then for acceleration, you take again the derivative, or 2 times derivative of the scalar equations for displacement. And you'll recognize that coefficient multipliers for the unknowns are the same. So multiplier for s dot here is the same as, or coefficient for s double dot. So a11, a12, a21, a22 are the same. What differ are the free terms. So the b1 and b2 would be different in the two equations. Okay. There's some, you can see there's like a term is 0 here and -1. So you could have columns, additional columns for a11, a12, a21, a22, and the b values, and implement Cramer's rule, or you just do this by hand and program directly what would be s dot and theta dot and s double dot and theta double dot in the spreadsheet the way I actually did. So you don't have, or you could, as I said, you could have would be 4 plus 4 more columns for a11, a12, ab1, a21, a22, b1, b2, and the other b1, b2 for accelerations. But the equations that occur here, or were programmed on these columns, for first derivative of theta 3, first derivative of s, second derivative of theta 3, second derivative of s, displacement of the punch, are the final equations. Okay. So, and of course, well, before it doesn't mean that you're copying the equations here. Make sure you draw this, rotate it, and I think I supply, or for you look at the homework. What homework was that that I said it helped with the project, and make sure you're referring to that respective figure and not for the crank slider mechanism operating was the slider horizontal. Okay, so I do have, let's see, it's here. I do have my spreadsheet. Let me see if I can make it fit the window, the recording window. Okay, so what's left in addition to the kinematics is to define this conditional force, the punch force, the corresponding torque using principle of virtual work, trapezoids to calculate the area under the torque curve, which is this is force graph, but I can switch to this one, and you can see they're pretty much the same or resemble, other than and of course the labeling, axis labeling is not valid. But what I did, I just quickly made it where we can observe the torque curve. All right, so and you saw the plots for punch displacement, first and second derivative of the velocity and acceleration of the punch, and then the other one would be the transmission angle theta 3. It's the transmission angle. It happens that they are the same, they coincide for the vertical mechanism. And this is a very or a more general organization of the spreadsheet, to where I can edit the crank radius, I can add the connecting rod radius, eccentricity. This will be positive value, negative value would be to the left of the y-axis. This is the punch rate, RPM of the crank. With RPM of the crank, I can calculate the omega, that is angular velocity of the crank. My spreadsheet has 720 or rather rows, that is data points, and the time increment is such that for the chosen 720 points, I'm covering a full crank rotation, one full cycle. I don't need more than a full cycle. Okay, and this was my way of doing this, with an equation. And then refers to the current point to the left, but you can do other ways you want. The crank angle is you get it by multiplying the time lapse from the time cell with the angular velocity. And this is constant RPM, constant angular velocity. Column for theta in degrees, that it's the independent variable or the x-axis values for these plots. Okay, I said B and C, and then S theta 3 and theta 3 in degrees, because you need it to judge the transmission angle. Okay, and then their time derivative of theta 3 first and second time derivative. All right, let's look at the force. So I have here defined the shear strength of the material, shear area based on the circumference and thickness, and stock thickness, as well as when the punch starts. So the S value, so when it's S value is 0.634, I have the punching starting. And let's go there. Okay, almost missed it. So 63354, 6.34. If you have very many points, like thousands of them, it's easier to match or closely approximate when the punch starts. From the available points, I mean, to the one that I choose here. And when the punch ends would be when the punch starts plus h. Okay, and maximum punch force. This is you go to the notes on flywheel, the chapter on flywheel design, and there I'm explaining how to you essentially define a linear function that's corresponding to the beginning and end of punch, so maximum force at the beginning and zero force at the end. Let me pause and bring that up. Alright, so in chapter 7, flywheel design, I'm discussing the punch press example, so very similar to help you with the semester project. And so if you choose when the punch starts and you have the thickness, you can find when the punch ends, and the force, the punch force, will have the equation of the punch force is that of a line that goes through this point F max and start of punch, and SF and zero force. Okay, so again, SS and F max, it's the order X and Y, not the other way, like I said earlier. So SS and F max and end of punch and zero. And this is the equation. It's a piecewise or curly bracket type function. So when I have here I'm saying crank angle corresponding to start of punch and end of punch. If theta is in between, then I have this equation, otherwise it's zero. But I could replace this with S being between S start and S finish, otherwise it's zero. Okay. Yeah, there's more information here. I'm helping you, as you can see, extra. So you have punch displacement and velocity, because those are needed to calculate the required crank torque using principle of virtual work. So you get the crank torque by saying derivative of punch displacement with respect to theta times punch force. Why is that? If you go back to what chapter was that on? I think on instant centers we discussed mechanical advantage. So you have a torque times delta theta. That's the work, infinitesimal work of the torque, is F times ds. So force times displacement, torque times angular displacement, the corresponding angular displacement, small angular displacement. You have ds over dt and not ds over d theta, but you can get it by saying ds over d theta, the angle, crank angle, is ds over dt that you have, and times dt over d theta, and this is 1 over omega. Okay, so you have 1 over omega, and you multiply that with ds over dt from your from the spreadsheet. So this is omega, and we have ds over dt. Let me box this. Okay, that goes into calculating and times force into calculating the torque. Under the torque curve, you then have to integrate. So you get next to the force column, there's the torque column. It refers to the force column in the spreadsheet and refers to the S dot column in the spreadsheet. And then use trapezoids to find the area under the curve. And then you divide the sum of trapezoids by the duration of the cycle. It's 2 pi, and that will give you the average torque. Okay, so let's go back to the spreadsheet, and the way I have it, if I zoom from here, it will stay the same, so no effect. But essentially, I'm using an if function from Excel, and as you can see here is if the punch is moving down, that is ds over dt is less than 0, and s is greater than start of punch and less than end of punch as the current value. Okay, then I have that linear equation like this one, and then if not, it's 0. Okay, you could, I think I have alternative spreadsheets to this where you're just so you have a column that can be either 0 or 1 based on this condition being true or false. Okay, so I could create a new column. Let's see, so I could have insert, and I could take this one, and this is 0 or 1, and I could have it like so. So equals 1 or equals 0. Okay, and expand it all the way down, and as you can see, it turns to 1 when the punch is in contact with the workpiece, and it's 0 otherwise. And then for the force, okay, here I could have, the equation. So how is it? So the equation of the linear variation of the force, and it's times this column. Okay, and nothing will change, but it's okay. So just to make it a little bit more easier to comprehend, more manageable, the equations in Excel, which so it's easier to debug the spreadsheet. Okay, and of course the equation exists like the way you have it here. So the line extends both sides of the equation of the line goes from minus infinity to plus infinity of s. But since I'm doing this multiplication, I'm setting forcing to 0 that force F outside of the when the punch is outside of the stop. Okay, and then torque. What do we do with the torque, or how do you get the torque? You remember is the force value, the this cell force value times ds over dt divided by omega. So principle of virtual work is essentially this, or rather this equation, T equals this equation. And all right, so this is for torque, and of course is zero when force is zero and has some non-zero values that go from a maximum to near zero when the punch occurs. And then finally the column for trapezoids to determine, to calculate the area under the torque curve. So we've used trapezoidal integration, and the one of the trapezoids, so it starts with 0, but the second trapezoid is going to be, and remember you work with like in homework problem, in sample problems that I did when we did flywheel calculation. So area of a trapezoid is well, we need a figure, so and decide what notations are, but this is it. So the difference that you see with C, this is the height of the right angle trapezoid, and if you rotate it 90 degrees, so we'll see a lower base, upper base of the trapezoid times the height is the difference between this value and this value divided by 2. So that's the area of one trapezoid. This is not trapezoidal integration, it's just calculating individual trapezoids. Okay. And then what I'm doing is, so you can calculate an energy. It's not listed here, but I could calculate the energy for one punch, which is this one, by simply by summing the trapezoids. Okay, so I have the trapezoids. Here the first is 0, and of course the others are 0 because I don't have a torque. And so what is this doing? Okay, so the way it's shown here, it's absolute value of let me delete only, oh, it's absolute value. Whatever, I keep this in the memory, and if you look here, there's a sum that goes from this cell, which is Q10, all the way to Q730. I have 720 points. So really, don't read it as the average anymore. So this is the energy, their energy per punch. Now, if I take the energy per punch and divide it by the duration of the cycle is 2 times pi. Okay. Then this is going to, for this, see the homework and the problems that I did on camera for sizing flywheels. So this is going to give me area area under the curve, that is total energy per one cycle divided by duration of the cycle. This gives you the average torque. Okay, so you have the average torque. If you know omega, you can calculate the power. Okay, so average torque times power, that's giving you the power of the crankshaft. In the project specifications, I believe I'm so no, but I'm making the recommendation now to consider some reasonable efficiency for the belt and for the gear transmission, and of course you would like to have some additional power available from the motor, maybe 40% more. You don't select the motor that is the minimum possible. Then that might not be able to actually start the press from rest when you have all the static friction and inertia to, or maybe it'll accelerate the press over a few good minutes. So in short, choose an electric motor that has 40-50%, could be double the calculated power by taking the average torque times angular velocity of the crank. Okay. On one hand, it has to be bigger because there are losses in the belt transmission and the gear transmission here. So you have losses between the motor shaft and the crankshaft due to the belt, due to the gear. There's additional losses in the bearing and friction, all that. But also you want to have extra power to be able to, say, punch larger holes as you, in many other instances, if you drive your car at home without launching it, like a normal person, you would need maybe not even 25 kilowatts. But of course, if you want to accelerate quickly, to pass, to tow a boat and all that, you'd need the extra power, maybe 5 times than the regular driving on a regular road. So I guess this is for part 1 of the project, up to selecting the motor. Make sure the motor is not a gear motor. Make sure the motor is reasonable for the job. On the photographs of punch presses you may found on internet, I have a few myself that I found. So if let's see, MSD, and there will be projects and punch presses and type and extra large icons. So I found there's a small press. Let's see, close all tabs, and some additional images. So what I was trying to say is, look at the motor. This is the figure that's also with the project specification. So this does not have a gear. It's not a gear motor. You may want to Google and recognize the gear motor by its appearance. So there's no gear reducer flanged between the motor body and the output shaft. I said 3-phase, not single-phase motor. Let's see, is this one where we can see the motor view? No, the motor is on the other side. But I'm sure you'll be able to find by Googling additional photographs of or documentation for punch presses relevant to your project. Okay, so 33 minutes of recording. I hope these were of use to you, and I wish you luck with your project.